And here we are once again. It is the Physics 105A lecture. Physics 105A video lecture 12. And today I have something very interesting. We're going to deduce the central force law from the orbital equation. From the orbital equation R of phi. And our goal is, of course, to deduce Newton's law of gravity from the orbital equation, but we'll have a general formula to get all kinds of interesting deductions. So I'm going to start out by setting up the entire formalism. This time, no effective potential for the first time in a while. But let's just go ahead and put up our whole Kepler problem. And that way, Kepler's law. That way everything will be pretty much self-contained in this lecture. Okay. So what did we have for the first law? Orbital equation R is equal to P over 1 plus E cosine of phi. So that we've shown is an ellipse. And good, we keep going here for a moment. Then we have the law of areas. We could say that was dA dt was equal to L over 2m, L being the conserved angular momentum. And then we have the law of periods, p squared proportional to a cubed. I'll just leave it like that. And as far as these definitions go, this was in plane polar coordinates. I'll draw a pretty exaggerated ellipse this time as part of our point of all this here, R of phi, 2a, 2b, the semi-minor axis, and then we have the definitions of a and b and p and e. So p is equal to L squared over m alpha, eccentricity root 1 plus 2e L squared m alpha squared. And then also we need to know a is equal to p over 1 minus e squared. B is equal to p over the root 1 minus e squared. So yeah, those should all be correct. And yeah, then there's a lot to do with that, and we've already done a lot. But this time, we're going to refer to these later on, or in fact, you guys will in your homework assignment, when it comes to actually deducing what is the central force law that gives us this law right here. Now, we did a poor man's version of it earlier on, where we did that deduction. So I'll actually do a little recall here. We did that deduction in the following way. We said for circular orbits, we had mv squared over r, simply by the definition of the centripetal force. And here's block this off. And then we said, okay, that's m 3 pi r over t squared, there's the r. And then all we had to do was replace that t squared with r cubed for circular orbits, and what we had left was then r squared over r to the fourth. So that was then proportional to 1 over r squared, because t squared proportional to r cubed. So for circular orbits, and of course this is only an expression that's good for a circular orbit. For circular orbits, we had that derivation. And that was enough to get us going, get us started. But now we want to do it for any ellipse, okay? Any conic section, basically. Now, I'll be erasing all of this, making sure that I had everything up there that I wanted. And that the whole theme is, of course, deducing this central force law. Yeah, could very well be that Newton did this way first, okay? Because the orbits of the planets were pretty circular. This kind of just lends itself to being done, but we want to get the exact one. It's going to be a very interesting thing. We're going to go back to some of our earliest work this semester, come back to haunt you. Okay, so I'll erase this and we'll get started. I'll go ahead and leave that theme up there. Yeah, okay. So the next thing I put up here is some discussion of the central force again, its definition. So central force, we said Newton's law has this form. Mass times acceleration. Like that. That's just the unit vector, of course, right? So F of R. So that's the central force law. And of course, we proved that angular momentum is conserved. So the motion is restricted to a plane, and that allows us to go to plane polar coordinates. So then I'll write here, recall for plane polar coordinates, and this is in the first couple of weeks of the semester, plane polar coordinates. We had vector R could be written R hat, R dot could be written R dot R hat plus R E dot E hat, etc. And we also had the R double dot, the second derivative, and I'm just going to write down what that result was. We can actually do it right here on the spot. It's not a big deal if you've done this a few times. Check your notes, or if you want, go ahead and leave some space in your notes, and you can fill in those calculations. But what we end up with is, for the acceleration, that is to say, for this equation here, we have m r double dot minus r v dot squared equals f of r, and the other component gives us r v double dot plus 2 r dot v dot equals 0. Okay, so let's look at this for a moment. So in plane polar coordinates, this is the meaning of it being a central force. You only have non-zero part on the right side for the radial equation. This is the transverse equation, and that's equal to 0. So this is the central force problem expressed in plane polar coordinates. Okay, there was just vector form, there's the plane polar coordinates. Okay, so far so good. This we've made use of before, and I'll go ahead and do that calculation right away. This is the one, right, that's associated with conservation of angular momentum, right? Because there's no, essentially we're saying there's no torque. Okay, you've got radial, transverse, there's no torque, that's why we had a 0 right there. So I'll go ahead and do this. If we do the time derivative of m r squared phi dot, just pulled that thing out of a hat, right? We don't even know where it came from. Say we do this time derivative, we get an m, a 2r, r dot, chain rule right there, phi dot, and then we get an m r squared phi double dot. If we pull out mr, we are left with what? 2r dot phi dot plus r phi double dot. Okay, those are 2 dots right there. And, okay, step back. What is that? That is that thing there, which is equal to 0. So this is where this angular momentum comes from, if you're approaching it from here. Okay. So mr squared phi dot is equal to 0. The derivative of it, mr squared phi dot, which is L, is equal to 0. So this is equal to 0. And therefore we can define this right here, L and R squared phi dot. Of course, we've had this definition already. But that's to make sure you see the relation that's in that transverse equation. Okay, so I can erase this now. And the next thing we're going to do is look at this thing in the light of this definition of L. Apparently we have M R double dot minus M R phi dot squared. Okay. So minus M R, and that's that phi dot squared is L squared over M squared R fourth is equal to F of R. So this is what we're going to be working with. Simplify it one more step here. Something else to be said there. Yeah, or equals F of R. Here we go. This thing isn't quite ready to be sent into action. We have to work on this for a little while longer. But what we're trying to do is find a way to take R of phi. We already have this expression, and then find out what is F of R equal to. So that's our goal. The R of phi, the Kepler problem 1, for example, the Kepler ellipse, we want to be able to plug it into a formula here and get the F of R out. That's the idea. So good. That's the plan. You know, I could just dump it in your guys' lap and say, take it away, but actually I'm going to keep working on this. Do a little bit of chain rule stuff here to get this thing going. Okay, what we need instead of R with respect to time is R with respect, differentiated with respect to the angle. So in order to deal with this expression, this equation here, what we're going to do is look at R equal to R of phi of t. Okay, so this is R of t, R of phi of t, and we have some chain rules. We can have R dot is equal to R prime phi dot, and we can have R second derivative is equal to R double prime phi dot squared plus R prime phi double dot. And so these are, let's go ahead and write these out actually. Okay. So what do we have here? We have equals dr d phi d phi dt. Okay. That's just the chain rule. Okay. That's the chain rule the way we've learned it. No problem there. This here is d squared r d phi squared. And when I did this derivative, I did d phi of r prime, which gave me r double prime, and then the inner derivative gave me the phi dot, but I already had one. That's why I have phi dot squared. d dt squared. Now this one, dr d phi is fine, but two derivatives of phi we don't have, two-time derivatives. We know what phi dot is, but not what phi double dot is. But I'm going to leave this thing here blank and fill it in as follows. I want to keep this guy up here. I've got a little room down here. So this d, so we have phi dot is equal to L over m r squared. Okay. We have that by virtue of the fact that L is a conserved quantity. Okay. So m r squared phi dot is equal to L. So now if I want to take the time derivative, I have d squared phi dt squared. Then I'm going to have L over m. I've got a 1 over r squared, so that's minus 2 over r cubed. Chain rule gives me a dr dt. Okay? So that has to be written L over m minus 2 over r cubed. And then the dr dt is right here. So that's dr d phi. D phi dt, but phi dot again is right here, so we have another L over mr squared. So this is the object that has to be plugged into my curly bracket there. We'll have minus 2 over r cubed. We'll have L squared over m squared r squared. And we'll have dr d phi, open curly bracket, dr d phi. So those are our ingredients. If we can make that replacement now with mr second derivative, with what's on the board there, then we will have this entire formula without any time, or rather with just special derivatives. And that is our goal. So let's see if we can do that. I'm going to put this formula up here, have it in front of me, and make some space here. Cubed equals f of r. Let's see if these can all be filled in. Okay, so let's see what we have. We have m. That r double dot would be, actually I didn't fill all these things in yet, did I? Well, let's give it a try. The r second derivative, that's the r double prime, d squared r, phi squared, and it was multiplied by d phi dt squared, which was L over mr squared squared. Okay. And then we had minus 2. Okay. I'll just get the minus 2 here, dr d phi, which comes in as a squared, so dr d phi squared. We have, I want to have it elsewhere. So I'm just going to pull out one factor of r here, and then I'll have r to the 3rd, 4th, 5th. Okay. So I'll have L squared over m r to the 4th. Running out of room here. And we just minus L squared over mr cubed. Squeeze it in right here. Minus L squared over mr cubed. So that actually does the trick. M squared. So now we have, cancel in, we get a common factor of L squared m r to the 4th. One factor, and cancel m squared. And then we have d squared r d squared minus 2 divided by r dr d phi squared. There's my L squared over m squared cancel the m or the fourth, good. And then here, minus r, and then r over r to the fourth, because we got r to the third. This is it. This is what we were looking for. I'm going to box it in here. That's the expression. So if we have r of phi, we got to put it into this machine, turn the handle, so to speak, and then find out what the force law is. Force of r. F of r. Okay, good. I'm going to clear up a bunch of board space. And I'll showcase this thing up here on the left, and we'll just work with it for a little while. Okay, so our force law, central force law, is going to look like this. F of r equals L squared over m r to the fourth b squared phi squared minus r. So you can plug that in and see what we get. Okay, now our goal and your homework is, of course, to plug in Kepler's law, Kepler's orbital law, and work through this. It's about a page worth of algebra, and then come out with 1 over r squared. But I'll do a couple of other examples that illustrate some stuff about this. Just to show you how one of these would be done. So the example we're going to do is r of phi is a constant times phi squared. We'll do two of these. R of phi equals constant times phi squared, and r of phi equals constant times phi first power. Phi squared has something for every one of these expressions, so we'll go with that one first. Okay, so what would this even look like? Here's our x and y. We're in the plane. What would this r of phi look like? R starts out 0 and grows as phi squared, so it's some kind of spiral. Okay. And if it were c times phi, it would be a spiral, also a different type of spiral. Okay. So as phi increases, this is just spiraling out and out. So what we have here, we have dr d phi is equal to 2 times c times phi, and we have d squared r d phi squared is equal to 2 times c. So what we're going to do is plug that in to our formula here. So we're just going to say, okay, we've got L squared over mr to the fourth. I'm going to point out you can always have this pulled out of this expression because L is a conserved quantity in the problem. Okay, so L is a constant in the problem, and you don't have to keep transforming. Although in the Kepler problem we will. We'll actually get rid of the L squared, but right now we don't have to worry about it. We've got L squared over mr to the fourth, and d squared r d phi squared is equal to 2 times c. We have minus 2 times 2 over r times, times 2c phi, the quantity squared, so 4c squared phi squared minus an r. And this we can just simplify. We've got actually we have 8c squared phi squared over this r, which itself is c times phi squared. So what we end up with here is 8c. So we have 2c minus 8c gives us a minus 6c. Okay. So what we're going to end up with is f of r is equal to minus L squared over M. This is my 8C right here. Yeah, minus L squared over M. I got this minus sign out here already. Minus L squared over M. So we'll have 6C over r to the fourth. And then this one here, that took care of that. When we multiply this one through, we'll just end up with minus 1 over r cubed. 6c over r to the fourth minus 1 over r cubed. Let's ponder this for a moment. Because you can't imagine plugging this into the integral we did the other day and coming out with something. I don't think so. But on the other hand, we start with a trajectory and find the force law. What I'm saying is, if we had known this force law, it would have been pretty hard to find that trajectory. Let me consult here. Yeah, that'll work. Oh, plus. Both of them had a minus sign. Actually, that's one of my points here. So I pulled out the minus sign for both. So what we're looking at is this spiral is an attractive, an attractive 1 over r to the fourth plus 1 over r cubed law. And that's interesting because it's an example of a general theorem that anytime your inverse law is greater than square, so any power greater than 2 in the denominator for a central force law, you're going to get trajectories that spiral into the origin. If we do another law here, c phi to the first power, we're also going to get something that spirals into the origin. You can also learn that by studying the effective potential, actually. Maybe you'd want to do that, even have a look at the effective potential in that regard. But yeah, the minus sign, remember this is the force law from the central force, so the minus sign means you've got an attractive law that's a combination of 1 over r to the fourth and 1 over r cubed. And if you release something here, spiral into the origin. And in fact, it'll turn into a pretty amazing tight and rapid spiral, because after all, it's spiraling into the origin, but the angular momentum is remaining constant, so it's going to probably get some diverging speed there at the origin or something impressive like that. Okay, so we've got a nice application of this. If you want, it's a slightly simpler one to just do r of phi equals c times phi. You just can now disregard the second derivative altogether. Similar result to that one. Okay, so what about your homework problem? Let me set that up for you, although it's been set up at the very beginning of the hour, but we now have this formula, and okay, this was just an application. So let's consult the original Kepler ellipse. This was a spiral. I'm just going to write here homework. From r equals e over 1 plus e cos phi. Deduce f of r is equal to minus alpha over r squared. And this L squared over m here, you're going to find that parameter p can be substituted for L squared over m alpha, and that's going to bring out the alpha in your problem when you're all done. Okay, so far so good. Let's talk a little bit more about this. As a homework problem, this is a great one. When I say deduce it from this plus all of the properties that go along with that ellipse that I had on the board at the beginning of the hour. You can refer to all of them. In particular, you're going to need that definition of your L squared over m alpha and stuff. when you substitute for P. What else here before I send you on your way? Yeah, well, as you take these derivatives, first and second derivatives and stuff, you're going to generate a little bit of complexity there on the board. You can see that dr d phi is already going to do something, the second derivative more. But have faith, okay? Just make sure you keep the errors to a minimum, and this will work out. And since you know what you're working towards, that'll help you monkey around with the algebra. That'll definitely help you there. And that will deduce the central for the inverse square law, essentially for all the conic sections, right? For the circle, hyperbola, parabola, ellipse. The ellipse is the one we've explicitly demonstrated to our own satisfaction. So that's what we're talking about. And again, remember, this will also be true for very, very elongated ellipses. Remember that problem with the time of infalling, the time to fall into a center of attraction, and how we could relate that to just an ultra narrow ellipse? Yeah, that's part of the mix here too. Definitely free of the circular orbit in this case. Okay. So yeah, that is the homework. And let me say one more thing about this homework assignment. Go ahead and include as much of this as you want. I hope in your notes you leave enough space to fill in every step. And even the original calculation that started from this expression and got us the radial and the transverse equations, if you go ahead and review that, it'll do you no harm either. Okay? Good calculation. Okay, I think I'm going to leave it here. This is the way I've been envisioning these lectures, about a half an hour now. About a half an hour. It's a good problem. So anything you do on this whole topic is a good review. And then when you get into this calculation, you'll be pleased as punch when you finally can check that off right there. Okay, so we're going to call it a day. Take great notes and see you next time.